My sincere greeting to one and all. I am Tamanna from BSc Chemistry Honors second year. Today I am here with my chapter Epoxides. Introduction. Epoxides are cyclic ethers having three membered rings in which oxygen is one of the atoms. They are also known as alkylene oxide or oxyrenes. The simplest oxide is ethylene oxide, epoxide or oxyrene, ethyl oxide or epoxyethane. In the common system, epoxides are called as alkaline oxides. In the UIPSC system, they are named as alkene oxides, epoxy alkanes, or oxyrenes. The common and IUPAC names of some epoxides are given below for the sake of illustration: ethylene oxide, ethene oxide, epoxyethane, oxyrene. Propylene oxides: propene oxide 1,2, epoxypropane, methyloxyrene. 2-butene oxide 2,3, epoxybutane 2,3, dimethyloxyrene. Cyclohexene oxide or 1,2, epoxycyclohexene. Synthesis of epoxides. First, epoxidation of alkenes. Epoxidation are usually prepared by reaction between an alkene and an organic peroxy acid, also known as pre-acid, or C double bond OOH. The reaction is known as epoxidation. Alkene plus pre-oxy acid epoxidation reaction will take and epoxide formation. Pre-oxy acids commonly used in the reaction are pre-oxyformic acids, pre-oxyacetate acid, pre-oxybenzoic acid, and chloropreoxybenzene acid. When a solution of pre-oxy acid and alkene in ether or chloroform is allowed to stand, epoxide is formed. For example, 2-butene plus pre-oxybenzene acid gives 2,3-dimethyl ethylene oxide, and cyclohexene plus pre-oxybenzoic acid gives cyclohexene oxide. 1,2-dimethylhexenes gives. It may be noted that epoxidation of alkene is a stereospecific reaction in which the stereochemistry of the substituent on the double bond is maintained. Thus, a cis alkene gives a cis epoxide and a trans alkene gives a trans epoxide. The reagent most commonly employed for epoxidation of alkenes these days is magnesium monopreoxyphthalate and MMPP. Mechanism. The mechanism of epoxidation involves the transfer of an electrophile oxygen atom from pre-oxy acid to alkene as depicted below. Second, from halohydrines. When halohydrines prepared by reaction of aqueous solution of chlorine or bromine with alkenes are treated with a base, HX is eliminated to yield a epoxide. For example, the formation of ethylene chlorohydrin and ethylene oxide. Mechanism. The base attacked the halohydrin to attract the hydrogen from OH part of halohydrin to form an alkoxide. The nucleophilic oxygen is of the alkoxide ion displaces the halogen from the adjacent carbon to form the epoxide as shown below. It may be seen that the reaction involves intramolecular within the same molecular nucleophilic substitution and is therefore treated as intramolecular Williamson synthesis. It should also be noted that as in SN2 reactions, the attack of nucleophile take place from the back side of CX bond. Third, manufacture of ethylene oxide. Ethylene oxide is manufactured by passing a mixture of ethylene and air under pressure over silver catalyzed at 475 to 675 Kelvin. Chemical reaction of epoxides. In contrast to acyclic ethers, which are chemically quick, insert epoxides shown high chemical reactivity. This is due to the highly strained nature of the three-membered ring system. Ring opening reaction of epoxide. In the three-membered ring containing oxygen, the COC bond angle and the CCO bond angle are nearly 60 degrees each. This large distortion from the normal tetrahedral angle of 109.5 degree causes very large strain in epoxide molecule. As a result, epoxide undergo a number of rings opening reactions quite easily. These reactions take place through the cleavage of one carbon oxygen bond and may be either catalyzed by acids and brought about by base or nucleophiles. Acid catalyzed ring opening. Just as simple ethers undergo cleavage of the molecule on reaction with acid, epoxide undergo ring cleavages on treatment with acids even under mild conditions. First, acid catalyzed hydrolysis. One of the most important cleavage reaction of epoxide is their hydrolysis to form 1,2-glycols. Hydrolysis takes place even in the presence of dilute minerals acid at room temperature. Epoxide to glycol. And for example, ethylene oxide to ethane 1,2-diol. Acid catalyzation reaction with alcohol. For example, the formation of 2-ethoxyethanol in presence of H2SO4. Third, reaction with halogen acids. Epoxide react with HCl and HBr to form chloro and bromohydrins. For example, the formation of ethylene bromohydrin. Mechanism of acid catalyzed ring opening. The mechanism of acid catalyzed ring cleavage may be illustrated by considering the hydrolysis of epoxides. In the acid catalyzed hydrolysis of epoxides, the epoxide is initially protonated by the acid. The protonated epoxide then undergo nucleophilic attack SN2 by water to cause ring opening by breaking carbon-oxygen bond. The reaction is completed by the loss of a proton as depicted below. Nucleophilic ring opening. Unlike simple ethers which do not undergo ring cleavage by a base or a nucleophile, cleavage of epoxide ring takes place even by such reagents due to the ring strain in the molecules. For example, when treated with OH negative ions at high temperature, epoxides ring get cleavage to form 1,2-glycol. Ethylene in presence of H2O negative gives ethane 1,2-diol. Mechanism of nucleophilic ring opening. The mechanism of nucleophilic ring opening is shown below with the help of basic hydrolysis of ethylene epoxide. The strongly nucleophilic hydroxide ion attack to the epoxide and displace the oxygen atom from one carbon by SN2 reaction. The product thus formed gets protonated to form a glycol as depicted below. The orientation of ring opening. Anti-addition. The ring opening of epoxide leads to the formation of product corresponding to anti-addition to the carbon-carbon double bond. For example, acid catalyzed hydrolysis of cyclopentane oxide yields trans 1,2-cyclopentane-diol. For example, cyclopentane oxide plus H2O in presence of H positive gives trans 1,2-cyclopentane-diol. Third, regioselectivity. Unsymmetrical oxygens can undergo ring opening in two different ways and generally lead to the different products in acidic and basic medium. In acidic medium, the nucleophile generally get attached to the more substituted carbon, while in the basic medium, the nucleophile become attached to the less substituted carbon. In the reaction of isobutylene oxide in presence of H positive and methanol, the major product formed is nucleophilic CH3O negative gets attached to more substituted carbon. Explanation. The difference in regioselectivity in acidic or basic medium may be justified as follows. In basic medium, the ring opening is an SN2 displacement by the nucleophilic of unprotonated oxygens, as in As in other SN2 reactions, the attack takes place at the less substituted or less sterilely hindered carbon. The less sterilely hindered carbon undergo SN2 attack. In acidic medium, the first step is the protonation of the oxygen of the oxygen rings due to the electron releasing group attached to the more substituted carbon. Positively charged oxygen attract the electron pair of its bond with this carbon to a greater extent than the electron pair of bond with the less substituted carbon. As a result, the more substituted carbon oxygen bond become weaker than the less substituted carbon oxygen bond. Therefore, ring opening take place preferably at the more substituted carbon oxygen bond, and the product contain the nucleophile attached to more substituted carbon. The weaker bond is preferentially attacked by nucleophile. Other nucleophilic ring opening reactions. First, reaction with Grignard reagent or organolithium reagent. Epoxide also undergo nucleophilic ring opening reactions with Grignard reagent and organolithium reagent. The product initially formed on the hydrolysis yield a primary alcohol containing large number of carbon atoms. The epoxide generally used in this reaction is ethylene oxide, and the alcohol formed containing 2 carbon atoms more than in the Grignard reagent. And propyl magnesium bromide gives 1-pentanol. Second is the reaction with alcohol. Reaction with methanol gives 2-methoxy-1-methanol. Third is reaction with ammonia, which gives 2-ammono-1-ethanol. Reaction with hydrogen cyanide. Reaction with HCN gives ethylene cyanohydrin. Reduction with LiAlH4. And this is the problem question. Write the formula and the name of the product of the reaction. Thank you.